because today we are going to go over the best kind of Newton's second law question, my favorite kind of Newton's second law question, because I'm not much of a geek that I have a favorite kind of Newton's second law question, but hey, you gotta be who you gotta be. Okay? So we're going to go over inclined planes today. Right? Inclined planes are another typical Newton's second law question. They are also one of the simple machines. Okay? And the simple machines make work easier. They don't make less work. That's impossible. Okay? But they make work easier. Right? So we're going to look at the forces involved in an inclined plane for the next couple of days. And then when we get into work and energy, we'll look at the energy involved in work and energy in an inclined plane. So let's say I do this. I put a 10-kilogram box on a 30-degree friction-free incline. What's it going to do?
Slide down.
Yes. Is it going to accelerate or move at a constant velocity?
Accelerate.
It's going to accelerate. Okay? If I put a 10-kilogram box, okay, that's like 22 pounds, on an incline of 30 degrees that has no friction, it will accelerate down that surface. Right? In fact, quite quickly. Why? What's pulling it down? Okay? Yes. The way I said that, yes, gravity is pulling it down, because that's the way gravity acts, straight down. What's pulling it down the ramp?
Well, it can't fall, but like it's slanted, so it's from the side.
Okay, you're right. Okay, it can't fall because it's supported by a surface. Okay, is that support nullifying some of gravity's desire to pull it straight down? It is. Okay, we call that the normal force. Okay, right now, me standing here, normal force and gravity are equal. That's why I'm not falling through the floor. Okay, gravity is pulling me down. For sure it is, okay? But I'm not falling because the floor is pushing up with an equal and opposite directed force. Now, if the floor gets angled, that's no longer true. Normal force is a reactive force to basically being pulled into a surface. But normal force can only act perpendicular to the surface that is providing it. So, if you have an angled surface, the normal force is angled. It's why if you stand on a hill, okay, or a really angled surface, you have a tendency to lean back in order to keep your balance. Okay? It's because normal force is trying to push you perpendicular, which creates a force that wants to make you go down the hill. That's what we're going to look at today. This is actually, anytime something goes down a hill, it is actually the vector sum of two forces. Okay? Sometimes 3 or 4. Okay? But we're just going to look at the simple situation today. So this 10-kilogram box, we've just said there's two forces acting. One of them is gravity. Which way does gravity pull? Straight down. Obviously the box can't go that way. Okay? But that's the way that gravity pulls. So I'm going to draw onto this a free body diagram basically. Okay? So that is the force of gravity. Can I calculate the value of that force of gravity? Right? Mass times 9.81. Luckily I picked an easy number. Okay? So 10 times 9.81 says that this force of gravity is 98.1 newtons. Okay. The other force acting on this box is normal force. And as we said, normal force is the reactive force of a surface, and it always pushes perpendicular to the surface. Okay? So that means then that normal force must go this way. Everybody all right with that? So now, normal force and gravity are not only not equal in magnitude, they're also not directly opposing each other anymore. So is that why the box goes down the ramp? It is, because there's a vector sum now to these two forces. How do I find the vector sum of these two forces? If I want to add any two vectors, what do I do? Is there a specific way that I draw them? How do I draw vectors if I want to add them? Lincoln? Tail to head. Okay, so I've got gravity pulling down, and I've got normal force. I drew normal force a little bit short. Just going to add a little tiny bit to that. I was guesstimating when I drew it. Okay, so I've got normal force, and I've got force of gravity. Now they're drawn tail to head. Okay, where does the resultant go? I've got those two vectors. Where should I draw the resultant? George, where should I draw the resultant?
Down.
Okay, like down this way, or like if this vector happened and then this vector happened, where do I draw the resultant? If this was the start and that was the end.
Like angled to the end of the second one.
Okay. What do you notice about the red line that I just drew and the ramp? They're parallel, right? Is that important? Heck yeah, it is. Okay, that's the result. That's the vector sum of those two forces. That's why the 10-kilogram block goes down the ramp. It has to, because that's what those two forces add up to, down the ramp. Okay, so that special little force that I just drew there, in this situation, because there's no friction, is the net force. But that force is always on an inclined plane, because anytime you put something on an inclined plane, it wants to go down the inclined plane because of a force we call force parallel. Okay, it's just two parallel lines drawn beside the F. Okay, the force parallel is always the vector sum of normal force and gravity. Now you're probably thinking to yourself, that's great, Coderre, I can calculate gravity, that's no problem, but how in the heck do I get normal force? Okay. Well, the answer is, most of the time you actually don't need it. But if this side is parallel to the ramp, is this triangle that I just drew a similar triangle to the ramp? Okay, if that's true then, what's this angle? 30 degrees. 30 degrees is what separates normal force from gravity. They're 30 degrees apart because of the angle of the ramp. Everybody with me there? Okay, so here's what you need to remember. This triangle is the same for any inclined plane. The hypotenuse is always gravity. The adjacent side is always normal force. And the opposite side is always F parallel. Always. Okay? That triangle is one you can memorize if you want. Okay? Or you can just treat every inclined plane problem and go, okay, draw the two vectors and draw them tail to head. You can do that too. Okay? But we're going to do a lot of inclined planes. That triangle is always the same. Okay? Now here's something I want you to think about. If this ramp gets steeper, what happens to F parallel?
It gets taller.
Right, it gets bigger. Okay, I mean, if I keep lifting it, if I keep making this ramp steeper and steeper, F normal is going to get smaller and smaller. F parallel is going to get bigger and bigger. Okay, eventually, if I get to this, well, F normal becomes 0 and F parallel equals FG. Okay, because now it's just going to fall straight down. You don't need a ramp. You're falling now if it's vertical. Okay, but even at 89 degrees, okay, there'd still be a little tiny bit of normal force. Okay, and a very, very big F parallel that would almost be equal to gravity. Okay, the lower this gets, the bigger normal force gets, because the closer to flat it's becoming, the more gravity pulls it into the ramp. Okay, and then the less F parallel would be. Okay, so that triangle just morphs. Okay, that angle changes. Okay, then the forces change. Okay, except for gravity. Gravity is always the hypotenuse, and it's always m times g. Okay, all right. So this question wanted the acceleration of the 10-kilogram box. So can I calculate F parallel if I know the hypotenuse is 98.1 and that angle is 30? Okay. So if I do that, I'm going to go sine of 30, because it's the opposite side, times the hypotenuse, 98.1. That should tell me then that F parallel should be 49.05 newtons down the ramp. Okay. Is that the vector sum of all forces, what I just did there, basically? I mean, I kind of circumvented it. I didn't actually add them together, but I used the triangle they would make to get one of them. Okay, so that's still the vector sum of all forces. Can I now find the acceleration? I can, because now this is F net. It's the vector sum of those two forces. So because of that, I can now do this. 49.05 divided by 10, right? So at a 30-degree angle, this is something to think about, okay? At a 30-degree angle, actually we only have, what, 2 significant digits there. You accelerate at half the rate of gravity at a 30-degree angle. Okay? If the ramp was frictionless, you would slide down that ramp at an acceleration half that of gravity. This happens when roads get really icy. Okay? It happened back a few months ago on the hill going up to No Frills there on Northwest Drive. Okay, it got like super icy one evening and everybody was sliding down the hill. Okay? I know because I was on the other side and I was like, ooh, physics, looking out the window because that's who I am. And I was like, okay. All right, so there wasn't very much friction and people were sliding down the hill because there was a net force acting on them down the hill that their tires could not counteract, and it ended badly. Okay? There was a pile of cars at the bottom. Okay, how would this question change if there was a force of friction on the ramp? Let's just say that they told us the ramp wasn't frictionless, but there was a force of friction of, let's say, 15 newtons. If you put a box on a ramp, which way is friction acting? Up the ramp. Okay, everybody all right with that idea? Because the box wants to slide down the ramp. Friction always opposes whatever the object is doing. If someone was pushing that thing up the ramp, which way would friction be acting? Down the ramp. Friction always works against you. Okay? It's your worst enemy. Always working against you. Okay? So in this case, that friction would be up the ramp. So I would have 15 newtons up the ramp, and I would have the other number I calculated already, 49.05 newtons down the ramp. Okay? Everybody all right with that? Basically, what I could do, if I make, let's say make friction purple here, okay? I got normal force, I got force of gravity, their vector sum is F parallel, and then I put the 15 newtons worth of friction on the head of that, okay? Going backwards, because that's what we do with vectors, okay? And then I would get a net force, okay, of this instead, okay? Well, will I get the same thing by just going 49.05 minus 15? Okay, that's generally what we do with inclined planes. We figure out what F parallel is, stick it on there, and then we know the box is going either up or down. And then we just draw all the up or down the hill forces. Okay? All right. So we're gonna work on a couple of those, okay? See how we do, just because inclined planes are kind of important questions, okay? When it comes right down to it, that's the trickiest part, that internal triangle. After that, it's forces up the ramp and forces down the ramp, and it's just like an elevator, really, okay? Once you've got the other forces figured out. Oh, no, that's a level frictionless floor. I don't want that one. Okay, this one. So I've got a 340 Newton box. That's a weird way to describe a box. What did I just tell you? Is that? It's not
The weight.
the weight, yeah. It's not the box's mass. That would be in kilograms. I just gave you the box's weight. What force is weight?
Down.
Okay, down, but it's what force?
Gravity.
Gravity, yeah, okay. So I just gave you the force of gravity. That simplifies your job a little bit, okay? So I've got a 340 Newton box being pushed up a 30-degree incline at a constant velocity, important, okay, of 1.5 meters per second. The applied force up the ramp is 200 newtons. What's the force of friction? Okay, draw the diagram, do the F parallel thing that we did in the last one, okay, see if you can get there. Okay, I'm just gonna put the picture up, just in case anybody's stuck. Okay, if you already have the picture and already rocking and rolling, that's great. Okay, that's the diagram, including the forces acting up and down the ramp. Okay, see if you can get what you need from there. So if I know the hypotenuse of that triangle, which is always the force of gravity, and I know the angle inside it, can I get the force parallel? Okay, so that's the next thing I need to do. Okay, force parallel, sine of the angle, this case 30 degrees, times the weight, 340, right, should give me 170 newtons. Yeah? I think that's right, right?
Yeah.
Okay, 170 newtons. So now I know that this force here is 170 newtons. How does that help me? If I'm going to find that missing force, I'm going to have to do vector sum of all forces, okay? Which means F applied, the 200 up the ramp, F parallel, the 170 down the ramp, plus the force of friction, okay? That's the thing I'm looking for. What do I not know right now?
F net.
I don't know F net, or do I? What is it?
0.
Right. Constant velocity. If the velocity is constant, that's why I wrote here, A equals 0. If the acceleration is 0, mass times acceleration, is 0. The net force is 0. It's moving at a constant velocity. That means the forces up have to equal the forces down. Okay, if there's 200 up, there's got to be 200 down. I've already accounted for 170. How big is friction? 30. Okay, just did vector sum of all forces, and did it in my head because it was 200 minus 170. Okay, 30 newtons worth of friction acting down. Okay, so in the end, what did I do there? I did that one trig calculation, and then I went 200 minus 170. Okay, it seems like there should be more to it than that. Okay, but there isn't. There's those catch words. Okay, constant speed, constant velocity, those have to become, maybe isn't the right word, they have to become triggering for you. Okay, I know that usually has a negative connotation to it. Okay, but those two words have to trigger you right away and go, oh, right, everything adds up to 0. There's no acceleration. All the forces add up to 0. I know something now. I know the net force is 0. And that's an important thing to know. We do all kinds of work in every Newton's second law question to figure out what the net force is. If they tell me constant velocity, they told me the hardest part of the question already. Okay? All right. Okay, try this one. Sledding down a hill is an inclined plane problem. So many things are inclined plane problems. And I don't know if any of you guys did the soapbox derby race here as a kid. Okay, that's an inclined plane problem. Okay, so in this situation, the child is sliding down the incline. Okay, we know that the incline is 25 degrees. Okay, this is the child, they're 50 kilograms. Okay, that's going to be FG, same as it always is. That's going to be F normal, which I won't need. Incidentally, you are rarely going to need normal force on an inclined plane. The only time you'll need that will be after Easter, when we've talked about friction and the coefficient of friction, and then you might have to use it in that situation. Okay, but like for 90% of the inclined planes, probably more than that, you won't ever use it. Okay, and so this side here will be F parallel, and obviously that angle then is 25 degrees also. So we've got friction resisting. Since the child is sliding down, friction must be acting up the ramp. Okay, and we are told that it's 150 newtons worth of force. What's this force? F parallel. Spoiled it. Okay, so that force is F parallel. Can I calculate that force? All right. So first thing I got to do, I got to calculate Fg. So I got to go m times g. I got to go 50 times 9.81, which is going to be 490.5 newtons. Okay, so now I know this side, 490.5 newtons. Okay, now I got to get F parallel. F parallel is the opposite side, so I'll go sine of 25 times 490.5. This work is always the same. Okay, these are always the things you're going to calculate, excuse me, on an inclined plane. So sine of 25 times 490.5. All right, so that force is 207.29, which makes sense because it is larger than the force up. It would have to be, or the child wouldn't be sliding down the hill. Agreed? All right, now I have the force down the hill and I have the force up the hill. What do I calculate now? Yeah, net. Okay. How many forces do I need to put together to get F net? 2. F parallel and force of friction. Here's a common mistake with inclined planes. People want to put these forces back in. Okay? Once you've calculated F parallel, you have already accounted for normal force and force of gravity. Don't bring them back. F parallel is their vector sum. They are already accounted for. So to get F net, that's simply going to be 207.29. Okay, that's F parallel down the hill minus 150 newtons up the hill should give me 57.29 newtons down the hill. Okay, so now I've done vector sum of all forces. Question wants me to calculate acceleration. F equals m times a. That's this part. So 57.29, okay, divided by the mass of the child, 50, okay, and we're not talking about a very big acceleration here. All right, so we're looking at two significant digits, 1.1 meters per second squared.
Downhill.
Downhill, right. Okay, are inclined planes patterned? They are, okay? That triangle's always the same. You're always gonna need the hypotenuse, you're always gonna need a parallel, okay? Sometimes a question can rearrange things. Maybe they tell you the acceleration and, you know, they ask you to calculate the angle of the head instead, so you gotta work backwards a little bit, okay? Sometimes that kind of stuff will happen, but it's always the same things. I'm gonna always need that triangle. I'm always gonna be dealing with gravity, parallel, and any other forces that might be in there, okay? That part of it is very, very patterned. All right, what do I get next here? Okay, I wanna go back to that vector question. Okay, so this is not an inclined plane. This is just two-dimensional vectors with Newton's second law. Okay, so you will need to draw a vector diagram and do X's and Y's here. Okay, give you guys some time to work on that one. Okay, question like this requires both types of diagrams. You need a free body diagram, you need a vector diagram. Now, the free body diagram is going to be kind of a bird's eye view because we're talking about something on a level floor that's being pulled north of east and south of east. Right, so we're going to be like we're looking from above on that object. So my free body diagram will, of course, as always, be a box. That box is 50 kilograms. That's due east, right? So my first force is going to be 35 degrees north of east and 150 newtons. And my second force is going to be 10 degrees south of east, 115 newtons. Okay, that's my free body diagram. Doesn't say there's, well, it says it's frictionless. So those are the only two forces acting on it. Nothing is resisting those two forces. I want to get the acceleration. I need the net force. Agreed? How do I get it?
Draw them tail to head.
Right, draw them tail to head, because I need the vector sum of all the forces that are acting here. So what I'm really going to do here, okay, is I'm going to take those. Right, there's going to be my first one. And there's going to be my second one. Something like that. I'll put the little dotted lines on now. So that'll be X, that'll be Y. X, that'll be Y, and then my net force, which is now the vector sum or resultant of these two forces, will look something like that, agreed? No different than what we did in the first unit with displacement vectors and velocity vectors. Force is a vector quantity. All right, so yeah, I've got to do some of that trigonometry stuff that we did in the first unit, that's fine. All right, so red X and red Y. So red X is going to be the cos of 35 times 150. Whoa. So 122.87. Okay, and then Y will be the sine of 35 times 150. 4. Okay, so those are both newtons. Then I gotta do the same thing with my green triangle. So green x, also the adjacent side, cos of 10 times 115. $113.25. And then y, the opposite side, so sine of 10 times 115. Jeez, what's going on? Okay, 19.97. Okay, now I've got all the x's and all the y's. The x's are both east, so I can just add them together to get the value for purple x. Right, so purple x will be the 122 and the 113. So 236.13 newtons. And then the y's, I do have to subtract those because one was north and one was south. So I'll take my 86 and subtract the 19. And so I've got 66.1 newtons. Okay, now I can find theta and I can find F net, because I forgot to label that earlier. All right, so F net will be Pythagorean theorem. So square root of 236 squared plus 66 squared, obviously with all of the decimals in place. All right, so we're looking at 245.19 newtons, and I need the angle as well, so that'll be 10 to the minus 1 of the opposite side. For me, that's the 66 divided by the adjacent side, the 236. So second 10 of 66 divided by 236. All right, 15.6 degrees. Okay, we only had 2 significant digits, I think, right? Yep, 10 degrees. Okay, so we had 2 significant digits. So we got to find the acceleration. Sorry, that's just the net force. I'm not done yet. Okay, so acceleration is F net divided by m, so that'll be the 245 divided by 50 kilograms. With all the decimals, obviously. Okay, 4.9. 4.9 meters per second squared at 16 degrees north of east. Or 74 degrees east of north if you drew the triangle the other way. Okay, a lot of work in that one. Okay, could I give you one like that on a unit exam? I probably will. Vectors are important. Okay, force is a vector quantity. Okay, tomorrow, make sure you have that SparkView app on your phone. We're going to need it because we're going to set up the pulleys and the carts and the tracks and yeah, we're going to make them go using pulleys and systems. So be ready for that tomorrow.